If you're watching this video, then you have one question and I'm here to answer it. Why quadratic regression? And maybe also, what is it? So we are about to start studying this, so we got to know that. Why do we need it? And why do we care? So a definition of regression itself from purplemath.com. I really like this, so I'm going to read this exact. The point of collecting data and plotting the collected values is usually to find the formula that can be used to model a presumed relationship. I say presumed because the researcher may end up concluding that there really isn't a relationship where he hoped there was one. For instance, you could run experiments timing a ball as it drops from various heights, and you would be able to find a definite relationship between the height from which I dropped the ball and the time it took to hit the floor. On the other hand, you could collect reams of data on the colors of people's eyes and the colors of their cars, only to discover that there is no discernible connection between the two data sets. The process of taking your data points and coming up with an equation is called regression. And the graph of a regression equation is called the regression line, or in our case, a regression curve. So the whole point of this is to take data that we have, usually real data, that doesn't really fit on a perfect line or a perfect curve, and come up with that equation. Okay, we use technology a lot to do this for us. Okay? But the simple case of regression is a linear regression. Now this is really useful when data clearly affects one another. So as one increases, the other one increases, or as one increases, the other one decreases. Or this picture that I've got right here is a scatter plot. Well, where the data is clearly going in one direction, that's great. Linear regression is fantastic. When things are just when they do affect each other that way, and they're so connected. The next kind of regression that's really common is quadratic regression, which we're going to be dealing with. And this is when things don't quite fit right. They just don't quite fit. Quadratic regression works great for modeling the trajectory of falling, thrown, or rapidly growing objects. And I say rapidly growing is to an extent. Because really, in a vacuum, which in physics, that's kind of what you care about. You don't worry about friction, you don't worry about heat, you don't worry about gravity. But in a vacuum, objects catapulted in the air, such as missiles, and if you're in the Army, you kind of care about things that go up and things that go down, or footballs, which you might also care about if you're in sports, they follow a path defined by a quadratic. So like I said, in physics, that is really useful. That's just a projectile motion is what it's called, and lots of things follow that. Okay. Also, another place that's used is short-term growth. So if something is growing over a short period of time, it actually might look, and you see this graph I've got right here, that's actually a quadratic, and that is data that's years, it's a population graph. But the point of regression is, again, to find relationships where we hope there is one. Okay? And so the moral of quadratic regression is that life is messy, and quadratics are a messier function that kind of matches that, that sort of chaos or disarray or just the other pattern that you see with projectile motion, things like that. So quadratic regression fits where lines don't, because lines are not always how everything goes. The third type of regression that's the most common is called exponential regression, and it's really good for long-term growth. Now, we're not going to deal with this right now, but eventually you will, and we'll talk about exponentials here toward the end of the year. But exponential regression is really good for long-term growth or decay. So things like radioactive isotopes. They start out with a certain amount, but every year or every so long, how many years, they decay. They kind of decrease at a steady rate. Or things that grow like populations over thousands of years. They follow this what's called an exponential, and you can kind of see a graph of these. This would be something like decay. It's decreasing at a steady rate. And this would be like population, where it's increasing, and this graph is actually over a long period of time, so it looks as growing very rapidly. But again, the point of regression is to find relationships where you hope there is one. So anything that continually increases or decreases can likely fit an exponential. It has a steady pattern of way that it decreases or increases. Okay, so kind of to recap, exponentials, we'll get to those, but those are really when things are always increasing or always decreasing. Linear regression is when things are nice, when things are perfect. That's the scatter plots we most often see. And then quadratic regression, which we're going to get into. So you'll appreciate this, hopefully, after seeing kind of some ways that it can be used. So the problems we're going to do are, well, they're real-life problems, real-world problems with real data that's not going to be real nice, so quadratic regressions work real great. All right, so hopefully this explains a little bit better what we're about to do. Let's go.